Hi. So in this week in Physics 201 lab, we'll be working on lab 6, which is simple harmonic motion. So if you were in the lab, you will be using a mass attached to a chain and then oscillate it and measure the time period that it takes to oscillate. So if you don't know what is a oscillator or a simple harmonic oscillator is, you may think about a simple pendulum in a grandfather's clock. So, like there's a hanging mass that's tick like over the time. Also, if you ever visited the Science Museum of Richmond, in the entrance, you'll be seeing a huge pendulum that's moved back and forth for a long time. And that's represent the Earth rotational period. So if you haven't visited the Science Museum of Richmond, please do that. But wait until it's open again. So in this lab, as I mentioned, so you need to have a chain that attached to a mass and you're going to swing it. Anyway, so if you look at this equation here, that's the main equation in the experiment. So you see it does have T equal to pi square root L over G. So this T represents the time period. So if you think about a pendulum which swings back and forth, so the time period means the time it takes to travel one full cycle. So if you think about like a pendulum start at this corner, then it swings all the way up and it's come back to the starting position. So the time the oscillator takes to go from one location and come back to the same location is called the time period. Then 2 pi, that's a number and a constant, and square root, and L is the length of the pendulum, and G is the gravitational acceleration. So if you are doing the measurements on Earth, it will be 9.8 meters per second square. So if you analyze this equation, where's the mass of the pendulum? It's not in here, right? So the mass is not included in the time period equation. That means the time period is independent of mass. So in the part 1 of the experiment, what you're going to do is you're going to hang different masses with a constant length. So you're going to use a 1 meter length chain, and then you're going to attach 50 grams, 100 grams, and as I remember, 500 grams, and then you oscillate it and measure the time period. So I'll be sending the data for that part 1 experiment. You may analyze those data. So you will be seeing like it's time independent. Then let's move on. So by the way, now think about like you're performing this experiment on moon. So what happened? Like let's say you use say a 1 meter length pendulum. Mass doesn't matter. So let's think about like 1 kilogram pendulum, which is attached with a chain which is 1 meter long, and you're going to perform the experiment on moon. So basically what happened is gravitational acceleration on moon is different from the gravitational acceleration on Earth. So when you go to the moon, the gravitational acceleration on moon is 1/6 of the gravitational acceleration on Earth. So basically it will be 9.8 divided by 6. So it will be a small number there, right? So the gravitational acceleration is going to be a small number. So when you are dividing something by a small number, you end up getting a larger number, right? So if you perform the same experiment on moon, the time period that the oscillator takes to swing will be larger. So it will take longer time to oscillate there. All right, so let's think about a pendulum. So here's a mass attached with a rope, and let's say the length of the rope is L. So in one particular point when it is oscillates to a little far away from the central location, so let's say this angle is theta. So like mass of the bob is represented by lowercase m here, and there will be a force on the mass, which is the weight of the this mass, right? So mg, mass times gravity, that's the weight of this pendulum, acts downward towards the ground. Are there any other forces acting on this? Yes, right? There should be tension acts on the along the rope, right? So there's a tension acts along the rope. So these are the only forces acting on it. So we're going to ignore the air resistance. As I mentioned, like we go to the simple model and we have some fixed conditions. So we ignore the air resistance over here. And also this is a point-like mass, so it is okay to ignore the air friction. Well, so with that assumption, we have mg acts downward towards the ground and tension acts along the line. Now, you need to draw a free body diagram, right? So free body, so there should not be a body in there. So you can represent this mass as a point particle. So you don't need to draw any other information. You only need to draw mass and the gravitational weight. The weight of the objects act downward and the tension acts along the rope, and this angle going to be theta. So this is a free body diagram. You don't need to put more information. You just represent that pendulum as a point mass. Okay, so you may complete that pre-lab question. Now let's move on a little bit more. So as you see here, mg, the weight of the mass is acting downward. So if you divide this force into component, like let's think about a force along the rope, so along this direction, and the force that's act perpendicular to the rope here. So as you see here, so I can divide this weight into two components. One is mg cos theta, cosine theta, which acts along the rope in the opposite direction, right? So here tension acts that way, and the weight component, which is mg cos theta, acts along this way. And the remaining component, which is mg sine theta, acts along this way. So if you think about this oscillator, it oscillates along this way. So mg sine theta is the force that supports this oscillation. So that's a force which keep the pendulum go around like oscillating. Well, so we call this as the restoring force, because when it's traveled to the other side, it's changing the direction and it's oscillates back and forth. So in the last week lab, you learn about the forces acting on a spring. This is very similar to that one. So the restoring force is always acts in the opposite direction to motion, right? It's in the negative force. So here, the restoring force is mg sine theta. And here, if you think about sine theta in your trigonometry, you know sine theta is the opposite over hypotenuse, right? So here, if you think about this angle here, this is theta, and the length of the pendulum is L. And let's say this length from here to here is d. So basically, that's the displacement of this pendulum, right? So it's displaced by d amount along this way. But if you imagine about real pendulum, it is not displacing along this way. It's make a curved path, right? So here we're going to assume that the curved path is kind of a straight line there. So it is another assumption. So this rule to be valid, this theory to be valid, this angle should be really small. Otherwise, we cannot think about this d, the distance over here is equal to the displacement of the object. Displacement means it's going in a circular path here, right? So it's this path. So that arc is equal to the length d. So here we are making an assumption which we say like theta is very small. Very small means it can be less than 10 degrees. So we call this as the small angle approximation. Here, let's describe sine theta. So we know like opposite of theta is d, and the hypotenuse is L. So I can rewrite this equation as mg d over L. So this is restoring force, which is mg d over L. And here, let's rearrange this equation. So mass, gravity, and length, those are constants, right? And the d is the displacement. So this displacement is there. And these are constants. So the restoring force is proportional to d. So if you increase d, the restoring force increases. If you decrease d, restoring forces decreases. So we call this as restoring force is proportional to the displacement. So I think you are ready to answer all the pre-lab questions. So please answer the pre-lab questions depending on this, what I explain on this video. All right, now let's look at the theory part of the experiment part 2, but I'll see you in a second video there. Otherwise, I'll be making this video too long.